Astronomers are on a scavenger hunt that started almost 100 years ago, searching for something right in front of their eyes. They know something's out there, holding galaxies together and sculpting the observable universe into this awesome shape, and they've given it a name: dark matter. The only problem is, no one has any idea what dark matter is. It barely interacts with anything except through gravity, it's invisible, and all attempts to detect it directly have failed. But maybe, just maybe, a giant moon orbiting Jupiter has been collecting evidence of dark matter all along. The problem with looking for dark matter is that we don't even really know what we're looking for. It's like trying to go on an Easter egg hunt if you've never seen an egg before. Also, the eggs are invisible and impossible to touch. But over the past several decades, scientists have come up with all sorts of ideas about what dark matter might be like. These days, one particularly popular hypothesis is that it's a bunch of tiny particles known as WIMPs that barely ever interact with light or regular matter. But very, very occasionally, a WIMP could collide with an atom and release a little jolt of energy. Assuming they actually exist, and this actually happens, we could detect those jolts. So around the world, scientists have built massive underground detectors full of heavy atoms like xenon. But after years of searching, they've had no luck. And that's possibly because they're looking for the wrong thing entirely. Some physicists have proposed that dark matter is actually made up of more massive clumps of stuff, which they call macroscopic dark matter. Unlike WIMPs, this stuff is supposed to be able to interact with regular matter, even violently. But these clumps would also be incredibly rare. Like, one might hit the Earth every 100,000 years. That's 1,000 times longer than the time humanity has even been thinking about dark matter, let alone actively hunting for it. And in between those hypothetical collisions, scientists have used process of elimination to figure out what we might be looking for and how we might find it. For one thing, we know roughly how massive a typical clump would need to be. And by roughly, I mean if it were less than an apple or more than a large asteroid, scientists would have already detected macroscopic dark matter in past experiments. That leaves a pretty big range in the middle, but it's better than nothing. And in a 2025 paper, one scientist came up with a new plan to look for it. The paper is still in preprint, meaning it hasn't been peer-reviewed yet, but this is the basic idea. If macroscopic dark matter is real, surely it's collided with objects in our solar system a bunch of times in the last 4.6 billion years. Earth's surface changes too much to hold on to evidence like that. But there are objects in our solar system that barely change, recording every strike to their surface across the eons. And we already have 2 space missions headed for one of them. Ganymede isn't just Jupiter's biggest moon, it's the biggest moon in the solar system. In fact, it's bigger than the planet Mercury, and its surface is old. A third of it is nearly as old as the solar system itself, and the rest is thought to be around 2 billion years old. So Ganymede is covered in scars of everything that's ever hit it in that time, including, just maybe, macroscopic dark matter. And the author of this 2025 preprint realized that if macroscopic dark matter does exist, it would leave a really distinctive scar. But before we get into more detail, we've got to keep the lights on with this completely unrelated to dark matter ad.
Merci, Babbel, for supporting this SciShow video. Right now, you're already crushing some popular New Year's goals by spending more time learning new stuff and less time doom scrolling. You're accomplishing all of that just by watching SciShow. And since you're off to such a great start, why not tackle another popular New Year's resolution, learning a new language? If connecting more with other people or taking on new adventures is on your list of goals for 2026, you can use Babbel to get there. Babbel is one of the top language learning apps in the world, and it helps people start speaking a new language in 3 weeks. That means by the time everyone else is giving up on their resolutions, you'll already be able to say, Je m'appelle Savannah, or whatever your name is. And if you try it out and realize that learning new stuff, doom scrolling less, connecting with more people, taking on new adventures, and mastering French was too ambitious for a single year, Babbel offers a 20-day money-back guarantee. Just write to customer service within 20 days for a full refund. So feel free to click the link in the description or scan the QR code for 55% off your Babbel subscription.
When a typical asteroid hits a rocky body like Ganymede, it usually shatters and leaves behind a shallow crater. But according to models, macroscopic dark matter would have to be enormously dense. I'm talking 1 billion times denser than water. The only place you can find stuff that dense in the known universe is in the cores of collapsed stars. But that's not the only extreme property this stuff has got. The macroscopic dark matter streaming through our solar system probably wouldn't be local. It'd be sailing in from somewhere else in the galaxy, traveling as fast as 270 kilometers per second. For comparison, your typical asteroid would crash into Earth going about 18 kilometers per second. So a clump of macroscopic dark matter wouldn't just burst into pieces when it hit the surface of Ganymede. It would punch into the moon like a bullet, and maybe even come out the other side. So what kind of evidence would this cosmic hit and run leave behind? Our 2025 paper gives us an idea by simulating an impact from a 2-meter-wide dark matter bullet. Based on the exact numbers the author used, the impactor would bore a hole roughly 5,300 kilometers deep, but Ganymede's average diameter is just a bit smaller than that, hence the potential for an exit wound. But Ganymede is also chock full of ice, both on and beneath its surface, so while the dark matter blob blazes through the moon's insides, it vaporizes the ice around it and sends a shockwave racing outward from the borehole. Thanks to some thermodynamic happenings we don't have time to get into today, this winds up ejecting material in the impactor's path, which we will be coming back to later. Next, pressure drops in the borehole as energy from the shockwave radiates through the moon for a couple seconds until it loses enough energy and peters out. It leaves behind a massive cavity, which at its widest measures 1.5 kilometers across. But the destruction isn't over. Almost immediately, debris starts falling inwards, starting wherever the pressure is highest and the hole is narrowest. But instead of just refilling the cavity, some of the infalling debris also gets blasted upwards in what's called a Worthington jet. You know what happens when someone cannonballs into a pool and a plume of water shoots up above them? It's basically the same thing as that. By the end, the impact event leaves behind not just a crater, but a bunch of debris from deep underground scattered in and around it. If the composition of that debris differs from what Ganymede is normally rocking on its surface, astronomers might be able to distinguish normal impact craters from those caused by macroscopic dark matter. And if they get really lucky, they might even be able to match these craters with exit wounds where the dark matter flew out the other side. Now, before anyone gets too hyped about this hypothesis, we can't do any of this crater searching just yet. It's not a job for a regular telescope to tackle. But in the early 2030s, NASA's Europa Clipper and the European Space Agency's JUICE will both reach Jupiter, and both will give us a clear look at Ganymede's surface at some point during their mission. If dark matter scars do exist, the probes should spot them. With all that said, we still don't have any amazing evidence that even suggests dark matter really is macroscopic, let alone that it left scars on Ganymede. But some of our most important theories started out as wild ideas, and when we're dealing with one of the biggest mysteries in science, sometimes it takes a wild idea to get somewhere. Or at the very least, tell us where not to look.